Hello, everybody. It's Thursday, 16th of April, and this is Nighttime Mathematics Radio. Well, it's another one of these evenings in this strange new COVID-infested world where all the classes have stopped, but the homework goes on and on and on. For the show's the same as ever. All you have to do is tweet your questions to Night Math Radio on Twitter, and I'll try to answer them here live on the air. We've got an interesting question that came in yesterday. How long would it take for everybody in the entire world to get COVID? And that's a fun question in a horrible sort of way, so we'll look at it right after the break. For the moment, if you have any questions, feel free to tweet them in. I'll try to answer them then. So we'll take a quick break for people to tweet in. Then it's on with Nighttime Mathematics Radio. Welcome back, everybody. This is Nighttime Mathematics Radio. A new question came in as well over the break, so I'll talk about that after the second break. But the first question came in is, how long will it take for everybody in the entire world to get COVID-19? And that's an interesting and very difficult question to answer. And keep in mind, this is Nighttime Mathematics Radio, not Nighttime Medical Radio, and not Nighttime Biological Radio. So if you hear anything here that's contradicted by anyone else who knows actual medicine, you should listen to them. I'm just going to treat this as a math question for the moment, an absolutely pure math question. Now, the one number that keeps getting bandied about in all this is this number called R0. And the idea of R0 is this is the number of people who each sick person will infect while they're sick, roughly speaking. It's a property both of the disease itself and what we're doing to fight it. So the fact that we're all hiding in our houses right now, frantically doing math homework, is actually a attempt to drop R0. And let's make a really stupid model for the moment to begin with. Then I'll talk about a better model right after that. If you can imagine a stupid model, imagine that people stay infectious for about 1 week. So if you let N of W be the number of people infected in week W, Then what's N of W plus 1? Well, it'll be equal to R0 times the number of people who are sick in week W. And if you assume that you're infectious for about 1 week, it's that minus the number of people who are infectious in week W. So it's equal to R0 minus 1 times the number of people infectious in week W. Now, what is it, R0 for COVID? I've heard numbers bandied around, which are all over the map, but the number I usually hear is around 2.3. That's higher than a typical flu, but it's much lower than monsters like measles. Measles has R naught of about 15, if you can believe that. So measles is amazingly infectious, which is why people freak out whenever there's a measles outbreak. Because a single person with measles infects 15 others, so the thing just explodes if it gets out into an unimmunized population. So you notice a few important things here. This tells us something about what numbers for R naught are important. If R naught is bigger than 1, the disease is spreading. More and more people have it in each following week. Because it means N of week the number of people in the next week will be the number of people in the previous week times something. If it's exactly 1, it stays about level. And if it's less than when people it will begin fading out. So let's take a look here. So let's take an example. For example, if say suppose N of week 1 is 10 people. What's N of 2? Well, if it's 10 times R naught minus 1. So if R naught is 2.3, that means in the second week, that's 1.3 times 10. So in the second week, 13 people have it. And it spreads outwards from there, growing inexorably exponentially. If it's 2, it passes through the population more or less smoothly. If it's 1, it starts to die out, which is sort of interesting. All right. So let's take a look at what we've got here. See, am I doing this right? Let me think for a minute here. This is the number of new infections. Oh, I'm sorry, I'm being silly because this is the number of new infections. So the number of infected people in the next week is all the people in the previous week gave it to R naught people. Oh, I don't need to subtract them off because they're already subtracted off. They don't come on. That makes more sense. So there we go. That makes more sense. So N of week plus 1 is equal to R naught N of W. So that makes more sense. So if R naught is 1, it's exactly level. Everybody gives it to 1 new person, then stops being infectious themselves, and it just stays level. If it's less than 1, it starts to die off. And that was sort of our goal. The one goal here is that you can imagine if we can get R naught below 1, it will sit and die off. Fewer and fewer people will get it. At the moment, it's 2.3. So if it starts at 10, the next week you have 23. The next week you have 23 times 2.3, which is 40 some odd or 50, and it just explodes outwards. In fact, let's switch over to a spreadsheet and see what this looks like. actually solve this. If you have n of week plus 1 is equal to r naught n of w, that's equal to r naught squared w minus 1. If you go all the way back to w, that's r naught to the w n of 1. So we actually have a nice solution here, which is that however many people have it in your first week, after w plus 1 weeks, it's r naught to the w if people have it. Well, how many people have it right now? How many people are currently infectious? You can look up the number of active cases, roughly speaking. Now, this is cheating a little bit, because remember, some people have recovered. So the number of people who have it right now is not the same thing as the number of people who will have it later. So, right now, this is the sort of thing you could look up on the internet. If I search, I Google for how many COVID cases, what I immediately get is all sorts of interesting numbers. Now, worldwide, we've had 2.1 million confirmed cases right now. Now, this is cheating. If you imagine that they're all sick right now, the question is how many people will have it next week? And the answer is, well, it'll be 2.1 million cases times 2.3. We can work that out. Let's go back to our spreadsheet real fast. I see I've lost my audio there, and I apologize. I know what happened, and I apologize. The thing I was trying to say while looking at that spreadsheet is that if you cheat, if you pretend that everyone who's infectious is infectious right now, then after about 11 weeks, the entire world will have had it. That's cheating for several reasons. First of all, that assumes R naught stays 2.3 all the way up, and it can't, because the more people who have it, the harder it is for the disease to find new people to infect. So R naught begins to fall off all by itself, even if it's spreading like wildfire. And the other issue is that so the issue is, as the thing spreads out, it can't stay exponential all the way up. The other thing, of course, is that it isn't going to stay 2.3 because we're all doing something. 2.3 is what it would have been if we all sat around having parties and going to movie theaters. And that's not what we're doing. We're all hiding in our houses doing math problems. So that makes R naught fundamentally much less as it goes up. Now, there's a more interesting model. Let's look at that one. There's this model that people actually use that's called the SIR model. And the idea here is you put the world population into three buckets. There's S, which is the number of susceptible people. These are the people who can catch the disease. So at the very beginning of COVID, this was presumably about 7 billion. It was everybody on the planet. I, and these are all functions of time, by the way. I is the number of infected people. These are the number of people who are infected right now. And finally, we have R, which is the number of recovered people. And by recovered, unfortunately, doesn't mean what you really hope. It mostly means people who got better. It also means a few people who died, but it's people who are no longer infectious for one reason or the other. Either they're no longer sick because they're better, or they're no longer sick because they're dead. Mostly it's the former. And then often, to work with this, what we really care about is not the number of people, but the fraction of the total population. So you usually use lowercase letters for this. You say S of t is capital S of t over n. It's the fraction of the population that's susceptible. You have I of t is the infected population over n. And you have lowercase r of t, which is the fraction of the population that's recovered. And these three have to add up to 1, because at any given time, everybody's either susceptible or they're either susceptible or they're infected or they're recovered. And you put together a really, really simple model. You say, okay, how do we figure out how many people are susceptible at the next time stage? Well, you say, what's the rate of change for the number of susceptible people? Well, it goes down because people who are susceptible become infected. And it's proportional to the number of susceptible people, because the more susceptible people there are, the more people can get infected. And it's proportional to the number of infected people, because the more infected people there are, the more people get infected. And this constant B, which is in here, basically says, how infectious is this thing? This is like the R naught we were talking about before. This is how quickly do infected people spread the disease to uninfected people. And how about the recovery rate? Well, infected people slowly recover, so the number of recovered people slowly is proportional to the number of currently infected, increases at the rate of the proportional number of currently infected people, and K is the rate at which people get better. So the longer it takes to get better, the longer you stay infectious, the smaller K is. And finally, because people are appearing or disappearing, this is obviously not true in real life because people are born, people die, but relatively small numbers of people. So you can make a guessing saying that everybody goes from one box to another. Nobody appears, nobody disappears. And that lets us make a model for the number of infected people. The IDT goes like, well, the people vanish. It's the people who vanish from the susceptible pool, so the people who get sick, minus the number of people who get better. So what does these look like? Initially, the number of infected people is very small, the number of susceptible people is very, very big. So originally, this begins dropping, and it drops faster and faster as people become infected, because you notice as people become infected, the number of infected people go up and the number of susceptible people go down. So these two numbers shift at the same time. And initially this term dominates, and the number of infectious people goes up. But as people get infected, they start recovering more and more, according to this equation. And so this term begins to dominate because the number of susceptible people drops as the people get infected. So it gets harder and harder to find new people to infect. The number of people recovering goes up, so the number of infected people begins dropping because people begin recovering. And so what you get is essentially three curves. You start with essentially everybody susceptible, and it falls off and then levels off somewhere else at some lower point. The number of infected people starts small, increases very rapidly, and then falls off again. and hits a sort of steady state as the number of people in the population, as you hit a number of people or a number of infected people's begins grinding out. Eventually it eats off to zero, because we're assuming people don't appear or disappear anymore. This slowly ekes down. And then recovered people start to zero, and then slowly increases, and eventually nearly everybody is either recovered or susceptible, and the infectious rate is very low again. That's the SIR model. It's much more complicated. You can see it's a differential equation in 3 variables. It's nonlinear because you've got S and I multiplied together. So it's the kind of thing you'd solve numerically. You figure out B and I by fitting. You figure out B and K by fitting them to the disease itself, and that will tell you that. And that's the kind of model people are actually using when they're working on this disease. And so the correct answer to how long it will take for everybody in the whole world to get COVID is forever. Because eventually enough people have had it and have recovered that the number of susceptible people begins dropping very, 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 very slowly. That's what people talk about when they're talking about what they call the herd immunity rate. Eventually, enough people will have been recovered and therefore not be susceptible to COVID, that eventually COVID will be unable to spread effectively. And at that point, we have what gets called herd immunity, and at that point, COVID will basically be over. What is our goal right now? Our goal is to make this peak happen as slowly and as low as possible, because we don't overwhelm the hospitals. That's why we're all sitting home doing math homework rather than going to watch movies. Basically, the reason we're staying home is we're trying to keep that peak low enough that people who are genuinely very ill can go to hospitals. Is this what we do forever? No. In fact, what we're hoping we don't have to do is wait for herd immunity. What we're hoping is that medical researchers will be able to develop a vaccine eventually, and at that point, we can get to herd immunity without having to all get it first. Or we could try to get tests. If tests get really, really good, we could go to a traditional quarantine and therefore make B very, very small by finding people who are sick very efficiently, putting them under a quarantine, and then that would drive B very, very low, or drive R naught very, very low, and that would again end the disease very quickly. That's what we're doing right now. The problem is right now we don't have either of those options. Right now we don't have enough tests to manage the real quarantine, and we don't have a vaccine. So what do? And the answer appears to be math homework. Okay, everybody, I'll be back after the break. We'll take a quick break. Then the question came in on Twitter. I'll answer it right after the break. Welcome back, everybody. This is Nighttime Mathematics Radio. We had a question come in over Twitter earlier, so let's take a look at that. This question looks like this, and I have to apologize. Since this question came over Twitter, it's a little hard to see where the square root goes. The question is either f of x is equal to the square root of 2x minus 3, or it's f of x is equal to the square root of 2x minus 3. I'm going to assume it's this one for the moment. And what the person was asked to do is graph this and say where it's increasing and where it's decreasing. And in this case, this is just a really nice thing about this. First of all, where can this even exist? Right? For this to exist, we're taking a square root, which means the argument of the square root, the 2x minus 3, has to be greater than or equal to 0. Because if 2x minus 3 is less than 0, you're taking a square root of a negative number, and while you can do that with complex numbers, nobody asks you to graph that, because that's just painful. So in that case, it says 2x is greater than or equal to 3, or x is greater than or equal to 3 halves. So whatever's going on here, nothing interesting happens to the left of x equals 3 halves. What happens when you plug in 3 halves? So you plug in 3 halves. 3 halves times 2 is 3. 3 minus 3 is 0. So the thing starts right there at 3 halves. Now, the interesting question here is, now, what you do next depends if this is a calc class or a pre-calc class or an algebra class. If this is a pre-calc or lower class, what you say is, well, 2x minus 3 is clearly increasing everywhere. You know what 2x minus 3 looks like, right? You can graph that. That looks like this. It goes through 3 halves, right at 0. It's got y-intercept negative 3. It increases with slope 2. It's just a line. It's a line you've plotted many, many times. But what do you do? And what about the square root here? Well, you sort of know what square root looks like. In fact, remember, a square root looks like a parabola kicked over on its side, because if you, going off of functions for a minute, just looking at this as a pure graphing problem, if y is equal to the square root of 2x minus 3, then where this function exists, y squared is equal to 2x minus 3. And if we could actually solve this, so 2x is equal to y squared plus 3, or x is equal to 1/2 y squared plus 3 halves. And we got there's a nice looking parabola, it's just on its side. If we're in the mood, we can complete the square to figure out what the vertex is. We don't care. What's more interesting, so we know what this thing's going to grow like. It's going to grow like a parabola. And the cool thing is, you notice 2x minus 3 increases forever. Right? Lines don't get a choice of whether they increase or decrease. They either increase forever or they decrease forever. Or they're flat. So since this is increasing everywhere, a square root doesn't change that. As you plug bigger and bigger numbers into a square root, you get bigger and bigger numbers out. They increase more slowly than the raw numbers. So this thing's just going to grow absolutely forever. Like a parabola kicked over sideways. I should say like the top half of a parabola kicked over sideways. Why can't you do the bottom half? Because this is a function. Functions are single valued. You put a number in, you get a number out. So we don't get the bottom half of this parabola, we just get the top half. Now, if this is a calculus class, you can prove this. And I'm going to assume for a moment this is a calculus class. If this is a calculus class, you can then say, okay, well, what's the first derivative of this thing? That is, what if f of x is equal to square root of 2x minus 3, what's f prime of x? And the answer is you can use the chain rule. The derivative of a square root is 1 over 2 square root of 2x minus 3 times the derivative of what's inside, which is 2. 2's cancel, so this is 1 over the square root of 2x minus 3. And again, wherever this function exists, this is a positive number. This has to be greater than or equal to 0. In fact, it has to be greater than 0. I don't even need the about equal to, because after all, that fraction can never be 0. It's 1 over a positive number. It doesn't exist right at 3 halves, you notice. Which means when it goes through 3 halves, the thing's going straight up. Which makes sense, right? This is the top half of a parabola. Parabolas are flat at their vertex. And this thing's flat, but it's flat this way. So it comes out with infinite slope, then arcs over. thing goes down forever. The bigger values of x you plug in, the smaller and smaller this fraction becomes. But it's always positive. So this thing is increasing forever as long as you're on the right side of 3/2. Okay, I hope that answers your question. And with that, this comes to the end of tonight's show. So I don't know whether the doing math about COVID makes you feel better or worse, but the short answer is COVID's going to be with us for a while. But eventually it won't matter as much. Because when enough of the population has become ill, or better yet, had a vaccine, then the possibility of a giant outbreak like the one we're seeing now goes down. Because after all, when more people have had it, it can't spread quite as quickly. The reason this thing's as scary as it is just because no one's had this before. That's the end of tonight's show. So in this weird world where the homework goes on and the math problems keep coming, but the classes have all gone somewhere else, feel free to tune in weeknights at 9 p.m. and I'll try to help you out. This has been Nighttime Medial Radio. Good night, everybody.